Hi, everyone. Thank you for attending today's webinar on measuring water in soil, part of the environmental research series by Campbell Scientific. My name is Connor Clayton. I'll be introducing today's presentation. This webinar is given by Dr. Dirk Baker. Dirk is an application research scientist in the environmental group here at Campbell Scientific. His areas of interest include ecology, agriculture, and meteorology. He has a bachelor's degree in wildlife biology and a doctorate in weed science, both from Colorado State University. This webinar was recorded previously, but we'll be opening a live Q&A after the presentation. Dirk will be joined by Jason Ritter, Senior Technical Support Engineer, and Chad Stevens, Technical Product Manager, to answer any questions. If you have a question for our speakers, please feel free to send it through the Q&A tab on your screen during today's webinar. If we don't get to your question during today's session, we'll be sure to follow up afterward. Today's session will consist of a 20-minute presentation by Dirk, followed by the 10-minute Q&A. The webinar will be available in its entirety after the session on our website, and be looking out for an email with a link to the recorded session within 48 hours. Everyone that registered for this will receive the email with the recorded session afterwards. So without further ado, here's today's webinar on measuring water in soil.
Hello, and welcome to this webinar on measuring water in the soil. My name is Dirk Baker. I'm an application scientist in the environmental group at Campbell Scientific in Logan, Utah. And before I get started, I'd like to acknowledge a couple of people for contributing to this presentation. Jason Ritter here at Campbell Scientific, and Dr. Colin Campbell with Meter Group and Washington State University. In this presentation, I'll start with some definitions of measurements in the soil and some of the common methods of measuring water in the soil, as well as strengths and limitations of each. Okay, so some definitions to start with. There are two primary ways of measuring water in the soil. One is water content, and the other is matrix potential. So water content, or better put, volumetric water content, VWC for short, is the volume of water per volume of soil, usually expressed as cubic meters per cubic meters water per soil, per total volume. So how much total water is present? In contrast, matrix potential is an energy state, so how tightly bound is the water to the soil, and this depends on a few things. The volumetric water, the total water present, but also the electrical and physical properties of the soil type. An easier way to think of this might be that this is the plant available water, or how much effort is needed on the part of a plant to get water from the soil. This presentation will focus on volumetric water content and introductory level understanding of some of the methods of measuring water content. Okay, so some of the methods, strengths, and limitations of measuring volumetric water content. Broadly speaking, there are a couple of different methods of measuring, at least common methods of measuring VWC in situ or in the field. One is resistance, and one is dielectric. And within dielectric, there are two at least common ways of getting to the dielectric, or the permittivity of the soil. One is capacitance, and one is in the time domain. Using resistance to measure volumetric water content certainly has the benefit of being simple. It just uses the soil as the resistor in a circuit. Incidentally, resistance is simply the reciprocal of conductivity, just as something to note. So by measuring one, you get both. The problem with using resistance is that as you apply a current to the soil, not only do the dipolar water molecules realign, as is shown in this figure, but the salt ions in the soil start to polarize as well. And so two factors are changing substantially as you apply this current. This figure further illustrates that complicating factor. So with different actual concentrations of salts or ions in the soil water extract, shown in different colors on this figure, you get very different relationships between the electrical conductivity of the soil and the volumetric water content of the soil, as shown in this figure. So remember that conductivity is a reciprocal of resistance, and so when you're measuring resistance, you'll get a very different volumetric water content depending on the actual salt content of the soil. So to summarize some of the strengths and limitations of resistance measurements, some of the strengths: they are cheap sensors generally. They're simple, as mentioned earlier. And so as such, they're good for simple demonstrations and home projects, science fairs and such. Some of the limitations: it is, like I showed previously, highly sensitive to ions in the soil, water. So in order to get water content, you have to assume that the total ions never change, which is clearly not the case, and usually have a pretty small sensitive volume. In contrast, sensors that measure the dielectric permittivity don't usually have the same polarization issues seen in resistance sensors. They still take advantage of the dipolar nature of water. They emit pulses, and the water molecules briefly realign, as shown in this graphic, and this causes a measurable change. There are quite a number of sensors on the market that measure dielectric permittivity that operate at a variety of different frequencies. And the lower frequency sensors do have some of the same salt sensitivity, ion sensitivity that resistance sensors do. But the higher end, higher quality sensors that operate at higher frequencies, say 1 to 2 gigahertz, they do not have that same sensitivity to salts. So the dielectric constant can be thought of as the ability to store charge of whatever medium is being measured. And by definition, air has a dielectric constant of 1. At the opposite end, at least for the purposes of this discussion, is water, which is usually around 80. It varies a little bit based on temperature and other factors, but for these purposes, we'll just call it 80. Other things in the soil have usually single digits dielectric constant, and so things like organic matter, the minerals in the soil, and ice, everything else in the soil is pretty low relative to water. And so it's changes in the water content of the soil that have the greatest impact on the measured dielectric constant or dielectric permittivity. To further illustrate that concept, we have just a graphic here. So as on the left here, we have a soil with very little water content. So you can see there's very little water in the interporal space of the soil here. As that then increases, it progresses along this spectrum of both water content and the measured permittivity. Okay, so let's talk about some of the common ways of measuring dielectric permittivity. One of the most common methods of measuring dielectric permittivity or dielectric constant is by capacitance. So this just uses the soil as a capacitor in a circuit, and then that charge storage is calibrated to the dielectric constant and hence then to water content. Okay, so some of the strengths and limitations of capacitance methodologies. It's simple circuitry, which makes it typically relatively inexpensive. Good accuracy and resolution, and often, this is the most common one that's been integrated into soil profiling probes. And it's usually a simple output, either voltage or SDI-12, which makes it easy to measure with a data acquisition system. Some of the limitations: it may be less robust because of components, but there are certainly high quality capacitance sensors out there. Can have a low operating frequency, which, as mentioned earlier, makes it sensitive to EC, similar to the resistance sensors. And it can also then be sensitive to soil texture. So it might take a soil-specific calibration. It can have temperature sensitivity. This isn't necessarily unique to this technology, but it's one of the limitations for this. It can also have a small sensitive volume. This doesn't necessarily always be it isn't always necessarily a limitation, because sometimes that's what you want. If it's a potted plant or a greenhouse situation where you want to make sure that the measurement stays within a contained area, that's then probably preferred. And it also depends on the sensor configuration. It's also sensitive voids in the soil, so air gaps next to the measuring elements, the rods, for instance, is going to compromise that measurement. This isn't also unique to these sensors. This is true for virtually all sensors out there. If they have air right next to the sensing element, then that's going to cause problems with the measurement, because it's not just the soil, it's air, which has a very low water permittivity. The other common method of measuring dielectric constant is time domain. And so in general principle, this is using the travel time of an EM pulse along a transmission line. This is usually also, it's worth noting that this is a broad sweep of frequencies, not a single operating frequency, which is an advantage as well. There are two general forms for time domain. There's water content reflectometry and time domain reflectometry with waveform analysis. Okay, so water content reflectometers operate with a transmission line oscillator, and that simply means that it's emitting these pulses along the rods, and those pulses then get reflected and come back, and as soon as that pulse comes back, then it triggers another one, so that's the oscillation. So, and then that time between pulses is directly related to the dielectric constant. Some of the strengths and limitations of water content reflectometry: it does have good accuracy and resolution, and usually a large sensitive volume, although this depends on how those rods are configured. It's usually a pretty solid, reliable, long-lasting sensor, and relatively cost-effective. There are SDI-12 versions available. In fact, this is probably the more common configuration of sensors in modern sensors anyway. And you'll often get electrical conductivity and temperature along with the water content. And this is true for a lot of sensors that are on the market now. Pretty easy to install, and long cable lengths are possible because of the SDI-12. So this means that you can get typically hundreds of feet of cable, depending on how many of these sensors you're connecting to the same data logger. Limitations include signal attenuation in lossy soil, and by lossy soil I'm talking about largely the high EC soils, and so that can cause an overestimate of water content, and you may need to do a soil specific calibration. And temperature sensitivity, this also interacts with the high EC soils, and so this can create quite a bit of work to develop your own soil specific calibration. And time domain reflectometry, or TDR, is the other time domain method of getting to the dielectric constant. And so this, similar to the water content reflectometry, emits pulses, and those pulses are emitted typically in a 3-rod configuration like that. They're emitted along the center rod and then detected coming back along the other rods. And because, as we've talked about earlier, the water content of the soil has the biggest, or the change in water content of the soil has the biggest effect on the measured dielectric constant or dielectric permittivity. That has the biggest effect on the measured signal there. And then a waveform is constructed from the return signals. So the waveform analysis component of TDR comes after those signals have been reconstructed into waveforms similar to what you see on the right here. And so the beginning of the rods on a sensor such as the one here below is represented by this hump in most of the waveforms, especially when there's much water in the soil. You'll start to see this first peak, and so that's the start of the rod right here. In air, this is by definition 1, and so this represents the actual length of the rods from end to end. As water content increases or other things are added, then this apparent end to the rods goes further out. And so this is an apparent length that changes because of water content. And so over here on the left, we have this equation So the LA, or the apparent length, is divided by the actual length, and that is directly the square root of permittivity. So it's a pretty direct way of getting to permittivity. Strengths and limitations of TDR with waveform analysis. So you get very good accuracy and resolution, and you get, so this is beyond the scope of this talk, but different forms of waveform analysis can get you EC, and so you get both with the same kind of measurement. Typically very high operating frequency, so you don't have the same sensitivities to the soil texture or EC. And you can get, it's also beyond the scope of this talk, but you can get other information out of the waveforms. And there are now some SDI-12 versions available, so it makes it far easier. Limitations, these are pretty expensive systems to set up and complicated. Now some of the recent products, especially the ones that are SDI-12, these are much less expensive and simpler to set up. And you still can get a high EC effect, so there is an upper limit to which where you just have too much loss of the electrical signal in those conductive soils, and so it can't find the endpoint in that waveform. This also depends on the probe geometry too. The longer the rods, the more subject to the high EC they are, and so shorter rods can be a way of dealing with this, or making it expanding the range of soils over which these sensors can operate. And also you can coat the rods, plastic, paint, that kind of thing, to eliminate EC from the measurement. And so there's just not that kind of loss to the soil. It also makes it so you can't measure EC, but you might get higher EC water content measurements out of it. You do have, with the full system, you have limited cable lengths, typically 25 meters maximum. And like I said earlier, it's a complicated system and usually takes a pretty high level of expertise to set up and use and do the analyses. Okay, in summary, there are two common methods anyway of measuring water content, the volumetric water content, resistance and dielectric. Resistance has the advantage of being pretty inexpensive, and there's lots of these on the market, but it's really not research or production quality, and it's very sensitive to conductivity of the soil, so saltiness of the soil. Dielectric, there are two main methods within dielectric, capacitance and time domain. These are often, more often research grade and less sensitive to EC, robust, and measure larger volumes. So then what? You might quite reasonably ask, what do I do with permittivity, or the dielectric constant? So there are a variety of empirical models to go from dielectric to VWC, and the most common amongst those are the top and Ledoux models. And so over here on the top of this graph, you see the two equations, and the references are there at the bottom for your information. So I'll just point out that the top model is a third order polynomial relating permittivity, here represented as epsilon, to the volumetric water content, represented as theta v. So, and then the Ledoux, you'll see that here it's a linear equation. It's a nice simple equation relating the square root of permittivity to volumetric water content. As you might remember, the square root of permittivity is that LA over L that comes directly from waveform analysis in TDR. So this is a common model used in TDR. And different models, the mixing models, which I won't go into great detail here, as well as the top and Ledoux, for most of the range of soil are really a pretty close match. You know, they start to diverge at the higher end, but for most of that range, there's not a whole lot of difference between the three. Also, it's worth pointing out that most good sensors will report both the dielectric permittivity and water content, and especially the SDI-12 versions do this. And so if you prefer, or if you need to do a soil-specific calibration, you can use the dielectric to develop that in the most correct manner. I hope that this has provided at least an introductory level of understanding of the common methods of measuring volumetric water content. As always, if you need help, there's plenty of additional resources, and you're welcome to reach out either through our website or call or shoot us an email.
Great. So we had some questions come through during that presentation. So let's go ahead and get as many of those answered as possible. So the first question we're going to have answered here is, can soil moisture sensors measure the liquid water in snow? Chad, could you answer that one?
You can certainly measure water content in snow with a soil moisture sensor. The liquid water portion has a dielectric just like it does in soil. So you can measure that. You cannot measure really the frozen portion of that water. So because frozen water has a dielectric, it has a permittivity that you would measure that would be very similar to soil. So you can measure the liquid portion, and it would give you some meaningful measurements there. But it is obviously going to vary depending on how cold that snow is and how dense it is, how meaningful that's going to be.
Great, thank you. Next question here, does temperature affect the water content reading? Dirk, could you answer that one?
Sure, so it has some effect, and some of the mixing models do try to account for that. But that's because the permittivity of water changes with temperature a little bit. It probably won't have a major effect for most measurements, at least in my experience. My colleagues might have more to add there.
Yeah, let me just throw this in there. The effect will be more noticeable near the surface, where you have greater temperature fluctuations throughout the day, and you might see something along the range of plus or minus 0.02 that's caused just by temperature. So it looks like your water content is changing throughout the day and the night, but it's really not. It's just the effect of the permittivity of water. And it's a bigger effect. The wetter it is, the bigger the effect is.
Great. Okay. Thank you, Dirk and Jason. Next question here. What is meant by sensitive volume and what determines sensitive volume? Jason, could you answer that one?
Oh, sure. Sensitive volume just means the volume of soil around the sensor where the water can be detected by the sensor. And that may change with water content. It may not be just a specific volume. So we talk typically in maximum and minimum sensitive volumes. The way that's determined, really, the simplest way is to have a sensor in water, and as you watch the reading as you raise it towards the air, and at some point you'll see a change in reading where it's obvious that the air is affecting the reading. And then you do the same thing from the other direction with the sensor in air, and you bring it down closer to the water surface until you see a significant change. There have been some other methods out there, for example, putting a sensor in frozen soil, and then as the soil melts, determining how much of that is through mathematically what the volume of ice is compared to the thawed soil on the outside. It can be complicated, but as far as what we do at Campbell Scientific, just using water and air is the way we've done it, and then verifying that in soil.
So the other thing that can be a rule of thumb is how far apart the rods are spaced and whether it's a 2 or a 3 rod design, kind of depending on the sensor, but that kind of gives you an idea of what the bounds are for how far the signal reaches and so how much volume is being measured.
Yeah, that's a good point. The rule of thumb is if you take the distance between the outer rods, that's about how far from each rod you can go and still be within the sensitive volume.
Okay, great. Thank you, guys. Next question here. Do you recommend any devices for soil solution sampling in response to rainfall events or groundwater table fluctuations? Dirk, could you answer that one?
I would actually defer to Chad or Jason on that one. I don't have a great answer off the top of my head for that.
Great. Chad?
Well, I think the answer would be a lysimeter, right? So that's the common way to measure that the soil solution. There's lots of lysimeters out there. Decagon, so Meter actually sells a nice in soil lysimeter that you can use. I think Jason's had some experience with that, some other lysimeters. Maybe he'd have some other things respond as well.
I'm trying to remember when I was going to Oregon State University, we had several field sites that had something called a passive capillary lysimeter, which essentially had a wick in it that would just draw soil solution into a reservoir. And I don't remember who manufactured that. The one Chad mentioned from Meter is also a good one. If you do a Google search for capillary lysimeter, that would probably get you in touch with the company that provides that product.
Okay, thank you. Next question here. Can you provide a quick overview of how the TDR can be calibrated to a specific soil, like you mentioned in the second to last slide? Dirk, could you answer that one?
Yeah, sure. And there's a white paper forthcoming that goes through that process. It wouldn't necessarily be exclusive to TDR. It would be really for any volumetric water content sensor. But you can use the most common way is to do measurements with a high precision scale of the soil. So you measure the soil, mix up a batch of soil with a amount of water, and measure that both with the sensor, and then take soil samples of known volume, and then measure the wet and dry weights of those samples of soil, and then repeat that for different levels of water content. And then you can develop that relationship. If it is one of the permittivity sensors, then it's probably the best approach to use the permittivity rather than the volumetric water content. But you could do it with the VWC as well.
Okay, great, thanks. We'll just answer 2 or 3 more here. And as I mentioned, if we don't get to your question today, we'll be sure to follow up afterward. What level of salts or the quantity will likely cause errors in your water content? Chad, could you answer that one?
Sure, Connor. That's a really good question. So the amount of salt, and I think this is the question that came from Hal. The amount of salts in your soil, kind of what it'll change is actually the conductivity. And it's that conductivity and it's that loss, the ionic loss, that causes problems in your sensor. So really the measurement of conductivity is going to give us probably more than just maybe a quantity of salts or the total dissolved solids. I can't speak for all manufacturers, but I can say this, that most of the ones that I'm aware of or that I've used and had experience with, anywhere between 3 to 5 decisiemens per meter is about the upper range of where most soil sensors are going to have adequate response. Get up above 5 decisiemens per meter, and a lot of them either have really large errors or they just stop responding.
Great, thank you. Okay, so this will be the last question, and it's how important is temperature calibration when using the CS616? Chad or Jason or Dirk, whoever could answer that one, go ahead.
All right. Chad's waiting to see if I'm going to talk first. The short answer is it depends on what you're doing with the data. The CS616, it's of course going to be sensitive to temperature because of the changing dielectric of water, but also pulling it in the opposite direction is the effective temperature on the electrical conductivity of the soil. So, for example, as it in a soil with low conductivity, a rising temperature would cause the reading to appear drier than it actually is. But in a higher electrical conductivity soil, that rising temperature will increase the conductivity and cause it to look wetter than it is. And so you have these two forces fighting against each other. And it's hard to say which one is going to have more effect because that's a soil specific thing. The deeper you get into the soil, the less these things are even a factor, but it's up near the surface where you need to be at least aware of those effects. And I'm going to throw in one other source of uncertainty, which is that we're taking a point measurement and soil is not homogeneous. So a very short distance away, you could be at a different water content. And so if you're taking a point measurement and applying it to a large area, you're going to have some built-in uncertainty anyway. So this is me going around and around saying it depends. But if you need something really accurate, probably the CS616 is not your best bet. You would want something like a TDR, and that way you don't have to worry about effects of texture and electrical conductivity. And Shaw, do you want to add anything to that?
Jason, I think you're right with what you just mentioned there. There's limitations to the reflectometers, which are like the 616, 655. Absolutely, TDR is going to be able to overcome some of those challenges, textural or maybe high EC temperature effects a little better. I think that the added measurements that are given from the CS655, conductivity and temperature, can really help, I think, to develop your own calibration, soil-specific calibration that can help as well. So that might be something to look into.
Great. Thank you for attending today's webinar on measuring water and soil. Please feel free to contact us on this contact info that I'm leaving up. Thank you for joining. Have a great day.